Okay, another week. That means another chapter and another set of quizzes are in front of us. If you haven't already done so, go to page 72 and take a look at the end of chapter summary. There's a bunch of definitions in there and some small explanations about what we're looking at in terms of the atom. Now, we'd previously said that the atom was the smallest indivisible particle. That is no longer true. It's been more than 100 years since the atom was split. And the early experiments, the book does a good job. There's some really nice diagrams and some historical explanations in there about what the discoveries were that let us know that the atom contained other particles. The first one to be observed was an electron. It's kind of the easiest one to dislodge. You can do it with a large amount of electricity. If you take two plates and you put a large voltage between them, they conduct. And if you pull those plates apart, a spark jumps from one plate to the other. If you put that inside a vacuum, a beam of light travels from one to the other. And that beam of light energy actually is electrons. And we found that they do everything that they're supposed to do if they're light. You can diffract them. They travel in straight lines. They cast shadows. But then we also discovered that you can bend them with magnets. That's strange. That's not something that light does. And that if you put a very, very small obstacle in their way, like some gold leaf, this light will dislodge the obstacle. So this beam of light energy that is the electron also has mass, also has charge, has a magnetic field. These are things that are not normal for other forms of electromagnetic radiation that we understand as light. So very, very special. So let's run through the big three subatomic particles that we need to know for chemistry. The three big particles are the proton, the neutron, and the electron. And if you get to the point where you're willing to admit that the atom is no longer the smallest indivisible particle, that protons are smaller than atoms, then you ask yourself, well, what are protons made of? It's mentioned in the book. It's actually in the realm of physics, not in chemistry, so I'm not even going to go there. Protons, neutrons, and electrons. Protons are given symbol P, neutrons are given symbol N, electrons are given symbol E, all lowercase. Proton was discovered by Rutherford. The neutron was discovered by Chadwick, and the electron, the first one to be discovered, was by Thomson. Now, protons and neutrons have approximately the same mass, so ever slightly different, and their mass is this number, 1.6 times 10 to the negative 24 kilograms. Remember, mass is measured in kilograms, and 10 to the negative 24 means I have 24 zeros, including the one that is before the decimal. So 0.0, all of these zeros, 1/6. That's the size of a single one of these protons and neutrons, subatomic particles. Really, really tiny. And we cannot be writing this out. This is too big, too long, won't fit in a calculator. And if you have to write all those zeros, you're more likely to make a mistake, which is why we use the scientific notation. Turns out protons and neutrons are approximately the same. So this amount we're going to call an atomic mass unit, an AMU. And protons and neutrons are the same. However, electrons are about 1/2000th the mass of a proton or a neutron. So you need 1839 electrons to be equal to the mass of one proton. So these electrons are really, really tiny. Protons have a mass or a charge of +1. Neutrons do not have a charge at all. Electrons have a charge of -1. And this is going to be important because the protons and electrons have opposite charges and atoms don't have a charge. That means that however many protons you put in an atom, you're going to have to put the same number of electrons. The number of electrons must match the number of protons in an atom because atoms don't have a charge. And we found that protons and neutrons, these bigger particles, are both located in a place called the nucleus. The nucleus was discovered by Ernest Rutherford. And if you can imagine this blob right here that's on the board, that's a sphere. That's an individual atom. At the very, very center of that atom, there is a speck that is 1/10,000th the volume of the entire sphere. Almost all of the mass of the atom is in this little speck at the center of the atom. I'm going to call that the nucleus. So the nucleus contains the protons and neutrons, and I need 2,000 electrons to be equal to the mass of one proton. So almost all of the mass of the atom is inside the nucleus, and then the electrons occupy the rest of the space, this open space right here. And it turns out that the electrons are whizzing around right about the speed of light in these orbits. And so we say that protons and neutrons are located in the nucleus, and electrons are in a cloud or an orbital that is around the nucleus. Okay. Why do we need 3 subatomic particles? Well, it turns out that they each do something subtly different. We're going to learn by looking at the periodic table that the number of protons in an atom gives the atom its identity. Okay. The periodic table has 110-ish atoms on it, and carbon is different than nitrogen. If you are a carbon atom, you have 6 protons in your nucleus. If you're a nitrogen atom, you have 7. So changing the number of protons in the nucleus changes the identity of the atom. It's like being asked if you've ever seen a 3-wheeled bicycle. No, you haven't, because 3-wheeled bicycles are called tricycles. By changing the number of wheels on the vehicle, I change the identity of the vehicle. Okay? And so that gives protons the role of giving the atom its identity. Now, because protons are positive, if I'm shoving all the protons inside the nucleus, this tiny little space inside the atom, all of that positive is going to repel because like charges repel each other. Different charges attract, like charges repel. And so the neutron, the thing that has no charge at all, acts as a spacer. So as our atoms get bigger, I'm going to need to put more and more neutrons in there to keep the positives away from each other, so that that positive repulsion doesn't rip the atom apart. And that action of spontaneously ripping an atom apart because the nucleus was too repulsive, that's called radioactivity. And we know that that's a naturally occurring thing. The electrons, well, the electrons have a negative charge and are very, very light and travel around on the outside of the atom. And because they're on the outside, when 2 atoms come together, it's the outside of the atoms that decide whether those atoms will interact. So the electron is responsible for all of the atom's behavior. Read that as electrons do chemistry. It's the electrons in an atom that perform all of the chemistry. This is a periodic table. I'm sure you've seen and heard of these before. This one is a modern one. It contains 118 named and numbered elements. And remember, an element contains only one kind of atom. We have determined that copper atoms are uniquely copper, and gold atoms are uniquely gold, and carbon atoms are uniquely carbon. They contain different numbers of protons, we know now, because protons give the atom its identity. So an element is just an atom that contains something that contains one kind of atom. Okay. Periodic table is an awkward looking shape, but it gives us some really good information. Atoms are compiled onto the periodic table in terms of their behavior, in terms of their reactivity. So everything in a vertical columns are called groups, displays the same chemical behavior. And I'm going to go with just an abbreviated version. I'm going to show you just the top part of the periodic table today. This is all we're going to be responsible for right now. Okay. So here on the board, I have the extreme left part of the periodic table and the extreme right part of the periodic table. There was a whole block of stuff in the middle that is a little bit too complicated to do in the second week of class. Okay? So, everything that is a vertical column is called a group. And everything that is a horizontal row is called a period. Groups are vertical, periods are horizontal. So that's like having a set of coordinates, that if somebody tells you a group number and a period number, you could locate where that atom is. And it turns out that when we look inside the box for any particular element on the periodic table, we get a little bit of information. Okay, everything in group 1 is a metal. Everything in group 2 is also a metal. In fact, almost everything on the periodic table is a metal. The only thing that's not a metal is way over here on the right-hand side, and in fact the top right-hand part of the periodic table, where we find things that are not metals. And we don't have an imaginative name for things that are not metals. We call them non-metals. Okay, so the periodic table is much wider than just the top part that we're looking at right now, but in its simplest sense, just those top groups with the extreme left and then the extreme right, they can be numbered 1 through 8. 8's going to turn out to be a magic number for us in chemistry. It's a special number that reveals that 8 electrons, combinations of 8 electrons in an atom, turn out to be super stable. This is something that electrons are going to aim for. Okay. Everything in group 1 shows the same behavior. Everything in group 2 shares the same behavior. Everything in group 3 shares the same behavior and is different from everything in group 4. But everything in group 4 shares the same behavior. But they're going to be different than things in group 5. But everything in group 5 shares the same behavior. So that's because it's because of the electrons. And every time we build these atoms out, we end at the same place. It's going to turn out that these numbers reveal the number of electrons that are on the outside of an atom. That if you are in group 5, like nitrogen or phosphorus, you're going to have 5 electrons on the outside of your atom. Okay, Let's look a little bit about what's going on inside any one of these individual boxes on the periodic table, because there is a lot to know. Inside a box, there are basically 3 pieces of information. There are 2 numbers, and then there is a symbol in the middle. Elements have symbols that are either a single letter, that is a capital, or 2 letters. And if there are 2 letters for the name of your symbol, then the first letter is capitalized and the second one is lowercase. Here, calcium is a capital C and a lowercase a. Carbon is just the capital C. Okay, so the elemental symbol tells us the shorthand, so we don't have to write the name of the element out every time, because some of them do have, especially the new ones, the ones that have been discovered very recently have very long names. And then these 2 numbers. The first number is an integer. Integer means whole number. When we look inside the box on the periodic table for any of the elements, one of those numbers is a whole number. That's called the atomic number, and the atomic number is equal to the number of protons. Okay? Hydrogen has an atomic number of 1. It has 1 proton in its nucleus. Helium has an atomic number of 2. It has 2 protons in its nucleus. Lithium has an atomic number of 3. Beryllium has an atomic number of 4. Boron has an atomic number of 5. Carbon has an atomic number of 6. And those atoms are placed on the periodic table in this kind of ugly shape that has a reason, sequentially. Sequentially in terms of ascending number of protons in the nucleus. So the atoms on the periodic table are listed in terms of atomic number, and the atomic number reveals the number of protons. The second number that's inside the box is always larger than the other number. Even if it's, in the case of hydrogen, it's fractionally larger, and is not an integer. This number has a decimal. It has significant figures. It has precision. That means this number has been measured. And what's going on here is this number is the number of protons plus the number of neutrons. The atomic number, the smaller number, is the number of protons. The larger number, the mass number, is the number of protons plus the number of neutrons. So if anybody ever were to ask you how many neutrons are in this particular atom, you take the mass number and you subtract the atomic number from it. And the difference between the mass number and the atomic number reveals the number of neutrons. So we've mentioned that the shape of the periodic table is irregular, but there are things that we can do to simplify that. Group 1 and Group 2 belong to this block. We're going to call that the S block. Then there's a block of metals in the middle that we call the transition metals. They contain things like chromium and nickel and iron that are called the D block. And then the non-metals over here on the right-hand part of the periodic table find themselves in the P block. And then there are a bunch of radioactive metals down here in the F block. The S and P block combined together give us 8 groups that constitute what's called the main block of the periodic table. And for general chemistry, that's where we're going to pay attention to. There is some beautiful chemistry going on in the D and the F block, but to learn the rules and the fundamentals about what's going on, we will stick to the S and the P. the 8 groups that are in the main block of the periodic table. The vast majority of elements on the periodic table are metals, and metals have things in common with each other. Metals conduct heat. Often when you touch a metal, it's cold, and then it pulls the heat away from your fingers. It conducts the heat away. Metals are known to be conductors of electricity. Metals are malleable and ductile. It means they can be hammered into shape and extruded into wires. Metals make a characteristic pinging sound when you hit them with that hammer. And metals have a specific type of taste that we call metallic. Conversely, non-metals don't. They don't do any of these things. They don't particularly conduct heat, so they don't conduct electricity. They typically can't be hammered into shape or extruded into wires, and they don't make pleasant sounds when you hit them with the hammer, and their taste is different. In the 21st century, we're not allowed to taste the chemicals anymore, but there was a point in time, not even that long ago, when you were allowed to taste the chemicals. It's a thing of the past now. Here's the important chemical distinction between metals and non-metals. Metals react by losing electrons. This is a process called oxidation. Oxidation is the loss of electrons. And everything in group 1 behaves the same way, that the metal loses an electron, and because electrons are negatively charged, the thing that gets left behind is left with a positive charge. Atoms that have a charge, because the number of protons doesn't match the number of electrons anymore, are called ions. And these, for the metals, are going to be called cations. Cations have a positive charge because the number of protons is larger than the number of electrons. Remember, for an atom, the number of protons is equal to the number of electrons. If we've just allowed our metal to give an electron away, now the number of protons, positive things, is larger than the number of electrons, negative things, inside the atom. And so our atom, now called an ion, is positive. Everything in group 1 loses 1 electron and makes a +1 charged metal ion. Everything in group 2, like magnesium, calcium, and beryllium, lose 2 electrons and make a 2+ charged cation. And everything in group 3, here's aluminum, loses 3 electrons. In this way, the periodic table is really fabulous to us because we can just look at that picture, find the element that we're working with on that particular time, and determine what kind of ion it's going to make, what kind of reactivity it's going to do. Now, non-metals do completely the opposite of what metals do. Non-metals react by gaining electrons in a process called reduction. And if I'm in group 7, here where fluorine, chlorine, and bromine are, the atoms in group 7 gain 1 electron and become negatively charged ions. Now the number of electrons is larger than the number of protons, and my negatively charged ion is called an anion. Everything in group 7 makes a 1- anion. Everything in group 6, like oxygen or sulfur or selenium, makes a reaction that gains 2 electrons and makes a 2- anion. If you're in group 5, like nitrogen or phosphorus or arsenic, group 5 atoms pick up 3 electrons and make a 3- anion. Oxidation by the metals, giving electrons away. Reduction by the non-metals, gaining the electrons, making positively charged cations from metals, making negatively charged anions by the non-metals. Now, there is something subtle and useful in the naming of what just happened. Atoms are just named the way that they are on the periodic table, but when you make an ion out of an atom, its name changes. Anything that goes positive ends in ium. Well, it turns out that most of the metals already end in ium anyway. Calcium, magnesium, sodium, potassium, chromium. These are all metals. They all end in ium. Ium tells us that's going positive. What happens to the non-metals when they get reduced, they change their name to ide. So chlorine becomes chloride, oxygen becomes oxide, nitrogen becomes nitride. Knowing that everything in the same group demonstrates the same behavior lets us take that information that we just learned about oxidation and reduction and apply it to the entire group. So everything in group 1 makes a +1 cation. Everything in group 2 makes a +2 cation. Everything in group 3 makes a +3 cation. Carbon and silicon at position number 4 find themselves in a place where it's too much effort either to lose that many electrons or to gain that many electrons. And they're going to hold off. They're not going to participate in this type of reaction. They're going to do something else that we'll see later. Everything in group 5 makes a 3- ion. Everything in group 6 makes a 2- ion. And then all of these halogens, group 7, fluoride, chloride, bromide, iodide, they all make a 1- ion. The elements that are in group 8 are called noble gases or inert gases. They already have 8 electrons on the outside of their atom, and that makes them incredibly stable. Stable is another way of saying unreactive, and so they're not participating in this at all. Okay, we're almost ready to make a bond. Bonding between ions makes compounds. Compounds are sometimes known as salts. Compounds are a result of ionic bonding, and I'm going to take metals from the left-hand side of the periodic table and non-metals from the right-hand side of the periodic table. I'm going to convert them into ions, and then I'm going to combine them until there is no residual charge. So if I wanted to make sodium chloride, I would find sodium here in group 1 with the 1+, and there's chloride with the 1-, and 1+ and 1- cancel each other out, leaving no residual charge, and therefore my chemical formula for sodium chloride is NaCl. So let's use the concept of ionic bonding to make some compounds. Sodium chloride. Sodium we found in group 1, therefore has a +1 sodium ion, cation, +1. Chloride was all the way over here in group 7. There is a 1- anion. The +1 and the -1 cancel each other out, and so I've made sodium chloride. This is a salt or a compound. And in naming ionic compounds, we name the metal first and the non-metal last. And we put a space in the name that tells us there is a gap in charge between these two ions, that this is ionic. So if I wanted to do the same thing and make magnesium bromide, I would look on the periodic table to find magnesium. Magnesium is in group 2. Everything in group 2 is a metal that undergoes oxidation to lose 2 electrons to become a 2+ cation. So here's my magnesium ion, and I'm going to combine this with bromide. So I look on the periodic table, I find bromine is in group 7, and because everything in group 7 undergoes a 1 electron reduction by gaining 1 electron to go negative, 2 pluses doesn't cancel out 1 minus. I'm going to need another bromide. So in this case, magnesium bromide is a compound that contains 1 magnesium ion and 2 bromide ions stuck together. So the chemical formula for magnesium bromide is MgBr2. Now, using numbers in chemical formulae, if the number is subscripted, that means it multiplies only the atom that immediately preceded it. So MgBr2 tells us this contains 1 magnesium and 2 bromines. Okay, we reserve the big number to tell us that a big number, non-subscripted number, tells us you multiply everything that comes behind it. So if you ever saw 2 NaCl's, that would mean 2 of all of this. Okay. So in cases where we're going to use combinations of numbers that are not 1, look for the subscript. Let's see a couple more compounds being made by ionic bonding, and hopefully this makes sense. Calcium oxide. If I wanted to make calcium oxide, I would look on the periodic table. All of the things that appear first end in -ium. Aluminium is the English pronunciation of aluminum, and I think you can sense that aluminum is misspelled, but continue to spell it this way until we fix it. Calcium being the metal, oxide being the non-metal, this being the positive, that being the negative. I'm going to go find calcium. It's in group 2, which means it makes a 2+ cation. And we're going to go find oxygen on the periodic table. It's in group 6, which means it makes a 2- anion. And 2 pluses and 2 minuses cancel each other out completely. So whatever it is that you write down at this point, that's correct. However unfamiliar it looks, if the numbers balance, what you've written down is correct. Potassium sulfide. Potassium is in group 1, which means it undergoes a 1 electron oxidation to make a 1+ cation. Sulfur is in group 6, which means it undergoes a 2 electron reduction to make a 2- anion. And 1+ will not balance both of those minuses, which tells me I need another plus. Now 2 potassiums have enough positive to balance the 2 minuses that belong to the sulfide, and my formula is K2S. Again, The subscript here multiplies only the atom that precedes it. So this tells me 2 potassiums for every individual sulfur. Aluminum fluoride, well, aluminum is here in group 3, which means it's a metal. It oxidizes to a 3+ cation. And fluoride is in group 7, which means it makes a 1- anion. And 1- is not going to balance 3 pluses. Going to need 3 fluorides for that. And so hopefully you can see that the chemical formula for aluminum fluoride would be AlF3. As well as simple binary compounds where one type of metal and one type of non-metal interact, it's possible for us to make polyatomic compounds. Some anions exist in combination with oxygen, and these are called oxoanions. Our book calls them oxyanions. Nitrate is NO3-. Charges are superscripted. So this tells us that everything in the nitrate only contains 1-. There is a subscripted 3. That subscripted 3 tells us only to multiply the atom that immediately preceded them. So nitrate contains 1 nitrogen atom, 3 oxygen atoms, and 1 negative charge. Sulfate is SO4 2-. Carbonate is CO3 2-. And hydroxide is OH-. Okay, it's not too much of a stretch just to take the rules that we already know and apply them. So if I wanted to make sodium sulfate, I would find sodium. It was in group 1, it made a 1+ ion. I would remember what sulfate is, SO4 2-, and then realize that that single plus does not have enough positive to cancel out those 2 minuses, meaning I need to find another sodium plus from somewhere. So the chemical formula for sodium sulfate is Na2SO4. This 2 multiplies the sodiums in front of it. That 4 multiplies the oxygens in front of it. Sodium sulfate contains 2 sodiums, 1 sulfur, 4 oxygens. Calcium hydroxide. Calcium is in group 2, makes a 2+ cation. Hydroxide is OH-. That 1- will not cancel those 2 pluses. I'm going to need another hydroxide. Now, I could write this one of 2 ways. I could write it this way, that shows the 1 calcium that I have, 2 oxygens and 2 hydrogens. And technically that's correct, but it's failing to convey to the reader that this is a hydroxide. And hydroxides are something that we need to pay attention to because they're bases. Bases are the opposite of acids. And so we need to store these responsibly in a place where we know that they won't come into contact with acids. And if I write them in a way that the reader recognizes that this is a base by showing the hydroxide, this makes more sense now. So Ca, and then everything inside the parentheses gets multiplied by 2. So the chemical formula for calcium hydroxide is Ca parentheses OH twice. So ionic bonding occurs between metals and non-metals. The metals become positive by oxidation, the non-metals become negative by reduction, and you mix and match those ions until the charge goes away. That is ionic bonding, and the result of ionic bonding is called a compound. I did manage to say somewhere in the middle there that carbon doesn't feel like doing ionic bonding because it's just too much effort to either gain 4 electrons or lose 4 electrons. And so carbon does something different instead. It's going to do a type of bonding that's called covalent. And we'll see covalent bonding in its own chapter later on in the book. And covalent bonding happens by sharing electrons, not by stealing and donating. And instead of making compounds, it makes things called molecules. And covalent bonding occurs not between metals and non-metals, but exclusively between the non-metals themselves. So when we hear that carbon burns in oxygen to make carbon dioxide is not a compound. Carbon dioxide is a molecule because carbon and oxygen are over here, and these are non-metals. The metals were to the left of carbon. And so this is a non-metal combining with another non-metal to make a molecule. And we'll learn much, much more about that later on. Chapter 2 concerns itself mostly with ionics.